Welcome to Lecture 2 of Geometric Physics 1. Today's title is Manifolds, Tangent Vectors, and Flows. Lecture 1 made a promise. Mechanics happens on manifolds, and phase space carries a canonical symplectic form. Today we begin paying that promise off. The reading is Frankel Chapter 1, pages 3 to 36, and Marsden and Ratiu, sections 1.8 through 1.10. Last time we made a claim and left it standing. Mechanics happens on manifolds, and the phase space T star Q carries a canonical symplectic form. We also met four systems we will return to all quarter: the free rigid body, the heavy top, the ideal fluid, and the Maxwell-Vlasov system. Today we make the word manifold precise. Then we build the two objects that everything later rests on. The first is the tangent space to M at P, which is the home of velocities. The second is the flow of a vector field. The flow is what time evolution means before any Hamiltonian has appeared. Here is the thing to hold on to. Every definition today is designed to be coordinate-free. Coordinates are allowed as a tool, but never as part of the definition. That discipline is what lets the same theorem apply to SO3 and to the volume-preserving diffeomorphisms of D. First section, configuration spaces are not R to the n. We start with the mechanical examples that force us out of flat space. Take three mechanical systems you already know. First, the double pendulum. A configuration is two angles, so the configuration space is S1 cross S1, which is the two torus. Second, the spherical pendulum, a bob swinging on a sphere. Its configuration space is the two sphere. Third, the rigid body with one point fixed. Its configuration space is SO3, the rotation group. None of these three is R to the n. None of them is even an open subset of R to the n, and yet all three share something. Near any one configuration, you can describe nearby configurations with n numbers. 2 numbers for the torus, 2 for the sphere, 3 for the rotation group. Crucially, the number n is the same everywhere on each space. That local flatness with a globally constant dimension is the entire definition of a manifold. Everything today is an unpacking of that sentence. Most configuration spaces arrive as constraint sets. You have big N ambient coordinates subject to some equations, and what is left over is the configuration space. Here is the key definition. Let F be a smooth map from an open set in R to the big N into R to the M. A point C is a regular value of F if the derivative dF at x is surjective at every x in the level set F inverse of C. Surjective just means the rank is M. The condition is imposed only on the level set, nowhere else. Now the regular value theorem. If C is a regular value and the level set is not empty, then the level set is a smooth submanifold of R to the big N. Its dimension is little n equals big N minus M. And at each point P, the tangent space to M at P is exactly the kernel of dF at P. This is the implicit function theorem wearing a different hat. Near P, you can solve the M equations for M of the coordinates in terms of the remaining little n. That gives a graph, and a graph is a chart. Frankel section 1.1c. First, the sphere, where f of x is the squared norm of x. Its derivative sends h to 2 times x dot h, surjective whenever x is not 0. So 1 is a regular value, the n-sphere is an n-dimensional manifold, and its tangent space at x is the orthogonal complement of x. For the rotation group, regard 3 by 3 matrices as R9, and the symmetric matrices as R6. Define f of A equals A transpose A. Then dF at A applied to H equals A transpose H plus H transpose A. Suppose A transpose A is the identity, take any symmetric S, and put H equal to 1/2 AS. Then dF at A applied to H is exactly S. So the identity is a regular value, and O3 is a 3-dimensional manifold, since 9 minus 6 is 3. The tangent space at the identity is the kernel of dF, the H with H plus H transpose equal to 0. Those are the skew-symmetric matrices, little SO3. SO3 is the connected component containing the identity. We will meet little SO3 again as a Lie algebra in lecture 14. Here is a mechanical example worth the time. Take a planar 4-bar linkage. 3 bars of fixed length pinned end to end with the 2 outer pins A and D bolted to the ground. The 2 free joints, B and C, each live in the plane, so the ambient space has 4 coordinates. There are 3 constraints, 1 for each bar length, 3 equations and 4 unknowns. Generically, 4 minus 3 is 1. The linkage has exactly 1 degree of freedom, as every engineer knows. But now vary the 3 bar lengths. At special values, the value stops being regular. The rank of the derivative drops. The configuration space is no longer a smooth curve, and it acquires a singular point where 2 branches of motion cross. So the regular value theorem is not bookkeeping. Its failure is exactly the mechanism by which real mechanisms lock, bifurcate, or change branch. Frankel section 1.1d. Second section, abstract manifolds. Now we drop the ambient space entirely and define a manifold with nothing around it. A chart on the set M is a bijection phi from a subset U of M onto an open subset of R to the N. That is all. A chart is a way of labeling part of M by N numbers and nothing more. Charts have to agree where they overlap. Take 2 charts, U with phi and V with psi. We call them C infinity compatible if 2 things hold. First, phi of U intersect V and psi of U intersect V are both open. Second, the transition map psi composed with phi inverse is a smooth diffeomorphism between them. An atlas is a family of pairwise compatible charts that covers all of M, that is, the whole construction. A manifold is a set plus an atlas. Now the point to carry away. All of the smooth structure lives in the transition maps. Transition maps are maps between open subsets of R to the N, so ordinary multivariable calculus applies to them without apology. And every definition we make from here on will be a definition that transition maps respect. If a notion is not invariant under change of chart, it is not a notion about M. So here's the definition. A smooth N manifold is a set M with a maximal smooth atlas of charts into R to the N, whose induced topology is Hausdorff and second countable. Those last 2 conditions look like bookkeeping. They are not. Without Hausdorff, the line with 2 origins counts as a manifold. On that space, solutions of ordinary differential equations stop being unique. A trajectory can run into a fork and pick either branch. So uniqueness of motion, which every physicist assumes, is a topological hypothesis in disguise. Second, countability buys us partitions of unity. We need those in Lecture 4 in order to integrate over M at all. Second countability also rules out uncountable disjoint unions. Smooth maps come for free. A map F from M to N is smooth if all of its local representatives are smooth. A local representative is psi composed with F composed with phi inverse, for charts phi on M and psi on N, wherever that composite is defined. A smooth bijection with smooth inverse is a diffeomorphism, and compatibility of charts is exactly what makes this independent of which charts you happen to pick. 3 examples. The N sphere needs only 2 charts. Project from the North Pole onto the equatorial plane, and then from the South Pole. On the overlap, the transition map is the inversion sending U to U divided by the squared norm of U, which is smooth away from the origin. Real projective N space is the set of lines through the origin in R to the N plus 1. There is 1 chart for each index I covering the lines where the I-TH coordinate is non-zero. There you divide the other coordinates by the I-FH1. Real projective space is compact, and for N even, it is not orientable. That matters in Lecture 4. Now the case we need. A rotation is an axis together with an angle between 0 and pi. Encode it as the vector theta times n hat, sitting in the ball of radius pi. Antipodal boundary points give the same rotation, so SO3 is real projective 3 space. And real projective 3 space is not covered by 1 chart. So there is no global coordinate system on SO3. Euler angles must degenerate somewhere. That is gimbal lock, and it is a theorem, not an engineering defect. Third section, tangent vectors. We have configurations. Now we need velocities, and there is no ambient space to take differences in. Here is the question. What is a velocity if there is no ambient space? In R to the big N, a velocity is a difference quotient of position vectors. On an abstract manifold, there is nothing to subtract. There are 3 standard repairs, and they all produce the same object. The first repair is curves. A tangent vector is an equivalence class of curves through P, where 2 curves are equivalent if they agree to first order in some chart. Compatibility of charts turns sum into any. The second repair is derivations. A tangent vector is a linear map V from smooth functions on M to R that obeys the Leibniz rule. That is, V of f g equals V of f times g at P plus f at P times V of g. The third repair is components. A tangent vector is a chart-indexed family of n numbers with a prescribed transformation law. Namely, v tilde I equals the partial derivative of x tilde I with respect to xj times vj. Mathematicians usually take the second, physicists usually take the third, and the first is the one to picture. Fluency means switching between them without thinking. Frankel sections 1.3 A through C. Whichever repair you choose, the theorem is the same. The tangent space to M at P is a real vector space of dimension n. A chart with coordinates x1 up to xn hands you a basis. The basis vectors are partial with respect to x1 at P up to partial with respect to xn at P. So every tangent vector V is Vi times partial with respect to xi at P, summed over I. Now change chart. The chain rule tells you how the basis vectors change. Partial with respect to xj equals the partial derivative of x tilde I with respect to xj times partial with respect to x tilde I. Run the same computation on components, and you get v tilde I equals the partial derivative of x tilde I with respect to xj times vj. That is the contravariant transformation law. Components transform like the coordinate differentials and therefore opposite to the basis vectors. Next lecture, the dual space appears, the cotangent space to M at P whose elements transform the other way. That is the entire content of upper versus lower indices. That is also the reason momentum is not a velocity. A smooth map ought to carry velocities to velocities, and it does. For f from M to n, the tangent map of f at P sends the tangent space to M at P to the tangent space to n at f of P. On curves, the class of a curve C goes to the class of f composed with C. On derivations, the tangent map of f applied to V acting on G is V acting on G composed with f. In charts, the tangent map is the Jacobian matrix of Fa with respect to xi. The chain rule becomes functorial. The tangent map of G composed with f at P is the tangent map of G at f of P composed with the tangent map of f at P. Collecting the tangent spaces gives the tangent bundle Tm, with projection tau m down to M. The bundle is a smooth manifold of dimension 2n because a chart on M induces a chart on Tm with coordinates xi and vi. In mechanics, Tq is the velocity phase space, the natural home of a Lagrangian L of q and q dot. But it is T star q, not Tq, that is symplectic. Now the rigid body, at the identity we computed the tangent space to SO3 to be little SO3, the skew-symmetric matrices. Write omega hat for the skew matrix built from a vector omega. Arrange it so that omega hat applied to U equals omega cross U. That is the hat map, a linear isomorphism from R3 onto little SO3. The hat map is why angular velocity feels like a vector when it is really a matrix. Now differentiate A transpose A equals the identity along a curve through a general A. You get A dot transpose A plus A transpose A dot equals 0. So A transpose A dot is skew, and the tangent space to SO3 at A is A times little SO3. Every tangent space is a translate of the one at the identity. That is special to Lie groups, and it is why T of SO3 is isomorphic to SO3 cross little SO3. The rigid body's velocity phase space is a product. And omega recovered from A transpose A dot by the inverse hat map is the body angular velocity. More in lectures 14 and 15. Fourth and last section, vector fields and flows. This is where dynamics finally enters, still with no Hamiltonian anywhere in sight. A vector field on M is a smooth section of the tangent bundle. Concretely, X assigns to every point P a tangent vector lying in the tangent space to M at P, and it does so smoothly. We write vector M for the set of all of them. In a chart, X is xi of x times partial with respect to xi. Equivalently, and often more usefully, a vector field is a derivation of the smooth functions. A derivation takes functions to functions and satisfies x of f, g equals x of f times g plus f times x of g. Two examples fix the idea. First, a first-order autonomous system of ordinary differential equations, x dot I equals xi of x, simply is a vector field. On a manifold, a dynamical system and a vector field are the same words for the same thing. Second, Newton's equation q double dot equals f of q and q dot is not a vector field on the configuration space Q. Newton's equation is a vector field on TQ, sending q and v to v and f of q and v. Phase space exists because second-order equations become first-order equations one level up. A curve C is an integral curve of the vector field x if C prime of t equals x evaluated at C of t. In words, the curve's velocity at every instant is the vector that the field prescribes there. The basic theorem gives three things at once. For each point P, there is a maximal open interval containing 0, call it IP, and a unique integral curve starting at P at time 0. Next, the set of pairs P and T, for which that curve is defined, is open in M cross R. And the map F, which sends P and T to the point reached at time t, is smooth in both arguments jointly, where both sides are defined. F sub t plus s equals F sub t composed with F sub s, and F sub 0 is the identity. That is the local one parameter group property. Each F sub t is a diffeomorphism onto its image, with inverse F sub minus t. This theorem is Picard-Lindelof, transported through charts. The chart independence is exactly the compatibility we insisted on earlier. And Hausdorffness is what makes the word unique true globally rather than merely locally. A vector field is called complete if IP is all of R for every point P. When that happens, the flow is defined for all time. F becomes a map from R cross M to M, and T maps to F sub T is a genuine homomorphism from R into the diffeomorphism group of M. There is a clean sufficient condition. Every smooth vector field on a compact manifold is complete. More generally, any field with compact support is complete. The standard warning is one line. On the real line, take x of x equals x squared. Its integral curve through x naught is c of t equals x naught divided by 1 minus x naught t. That escapes to infinity in finite time. Nothing is wrong with the vector field. The non-compactness of the real line is what lets the solution escape. Mechanically, incompleteness is a collision or a blow-up. The n-body problem is a perfectly good Hamiltonian system whose vector field is not complete. The reason is that its configuration space is R to the 3n with the collisions removed, and that is an open set. Regularization theory is the study of when the flow can be extended across those punctures. Now a theorem that is easy to state and easy to underrate. Suppose x at P is not 0. Then there is a chart around P with coordinates y1 up to yn, in which x is simply partial with respect to y1. In those coordinates, the flow just adds t to the first coordinate and leaves the others alone. That is the straightening theorem, also called the flow box theorem. Read it carefully. The theorem says that locally, away from equilibria, every dynamical system in the universe looks like uniform translation. There is no local invariant to find. There is nothing to compute. So where does all the interesting behavior go? It goes to two places. The behavior lives at the zeros of x, which are the equilibria, where the theorem does not apply. And it lives in the global structure of the flow. Recurrence, closed orbits, invariant tori. None of those is visible inside a single chart. Straightening says local dynamics is trivial. So everything a physicist actually cares about, including all of stability theory and all of reduction, is a statement about global structure or about degeneracies. Frankel section 1.4c. Let us collect what we built. Manifolds defined by charts and compatible transition maps. The regular value theorem, which turns constraint sets into manifolds. SO3 as a three-dimensional manifold, which is real projective 3 space. The tangent space to M at P in 3 equivalent guises, the tangent bundle Tm, and the tangent map. The tangent space to SO3 at A, which is A times little SO3, and the hat map, and vector fields, which are dynamical systems and their flows. Notice what is missing. Nothing we have built knows about energy or momentum. We have made the stage, not yet the play. Lecture 3 supplies the dual side. Covectors, the cotangent bundle T star M, the one form theta equals PIDQI, and then tensors and exterior forms. Lecture 4 does integration and Stokes and Maxwell. Lecture 7 brings omega equals minus d theta. And Hamilton's equations, the interior product of XH with omega equals dH. That is the flow of today's lecture, now generated by an energy function. For Lecture 3, read Frankel sections 2.1 through 2.7. Pay particular attention to section 2.3 on the cotangent bundle and phase space. That is where mechanics enters the geometry. Problem set 1 is due at the start of week 2.